In the past several decades, our world has witnessed an almost unbelievable explosion of technology, an endless revolution of change, stimulated by new knowledge and fueled by innovative techniques. This unrelenting pressure of progress has forced us to realign our basic concepts and has propelled us forward in search of a better way. Kearney Trecker has long been recognized as the leader in the creation of unique metalworking systems designed to provide solutions for specific needs. In the 1950s, a frequent application of this technology was expressed in machining concepts designed to produce large quantities of the same part. With the use of dedicated tooling, automatic transfer systems, and the simultaneous machining of two or more sides of a workpiece, cycle time was dramatically reduced. However, the advantages were minimized by the inflexible nature of the system, since almost any change in part size or shape required costly machine rebuilding. These machining systems made a profound impact on the metalworking industry, and a new word emerged to describe them: automation. Using this breakthrough as a base, Kearney Trecker concentrated its research on extending the benefits of automation to small and medium lot size manufacturers. In the late 1950s came the results. The world's first tape-controlled machining center. With its automatic tool changer and pallet shuttle, the machining center concept provided flexibility never before possible. Now a variety of parts in small lot sizes could be produced economically on a single machine. And with this production efficiency came important corollary benefits. Management could be far more responsive to changes in lead time and factory loading schedules. Huge outlays of working capital tied up in partly finished parts could be substantially reduced. Engineering changes could be made quickly and inexpensively by simply changing a tape program. However, even with all these obvious benefits, the machining center system was limited to small lot production. It could not be expected to compete cost-wise on a part-for-part basis with fully automated systems. The obvious goal then was a combination of the best of both concepts. Find a way to incorporate the flexible advantages of machining centers with the high production rate of combinations of single-purpose dedicated modules. Kearney Trecker's ongoing search for a better way provided the answer with massive, flexible metalworking systems. Here's one example of this new technology: a giant multi-station complex designed to process large housings in two different styles. It performs operations on a family of 12 cast steel parts in 6 different sizes, ranging from about 5 feet to 7 feet. The system also has built-in flexibility to machine larger parts if required, parts with an overall length of about 9 feet. This Kearney Trecker complex consists of 7 stations in a sequential line, working in conjunction with a pallet return system. There are individual controls for each machining module, making each one an independent, standalone machine. Isolation of each machine module was achieved with the use of a software package called PAL, or Programmable Application Logic. PAL monitors and controls basic functions such as shuttling, indexing, and clamping, and initiates a machining program. In essence, it is the communication link between machine controllers. In addition to PAL's basic information, the machine controller stores specific part programs, regulating feeds, speeds, and dimensional data. Program data is loaded into the memory either by keyboard or punch tape. The pallet return system has its own separate control called PLC, or Programmable Logic Control. Through software, this control is interfaced with Station 2 and 6. Only one operator is needed to monitor this entire manufacturing system. The operator also loads and clamps workpieces at Station 1. A special fixture design prevents loading the wrong part. After loading, the part is shuttled to a pallet-ready position. Pallet-ready positions are located between each machining module, compensating for differences in cycle time. The pallet is held at this staging area or buffer station until the machining module has finished the previous part. When the station is clear, PAL identifies the part, selects the correct part program, and shuttles the workpiece onto the machining station. The challenge in the first operation was to rough and finish mill 2 pads on the top of the front housing. Kearney Trecker solved this problem with a 50 horsepower single spindle vertical milling module, a standard unit of dependable design proven in many similar applications. A 3-position quill provides vertical positioning with 2 forward positions for rough and finish cuts and a return position to prevent cutter retrace over the finished surface. After the completion of machining at the first pad, the machine automatically positions to mill the second pad. In parts of this size, non-uniform castings with inclusions and excessive stock have always been a problem in automated machining. To solve this difficult situation, Kearney Trecker equipped this milling module with a form of adaptive control. With this capability, the machine senses changes in cutting conditions and automatically reacts by slowing the feed rate, maintaining a constant 50 horsepower spindle load. Thus, adaptive control maximizes machine utilization. If for some reason cutting conditions deteriorate beyond the capacity of the adaptive control compensation, the entire unit shuts down, preventing damage to both cutter and workpiece. This entire sequence of operations functions without the assistance of the operator. Upon completion of the milling operation, PAL checks the condition of the next pallet-ready station. If unoccupied, PAL moves the part to it. A 5-button workpiece code reader is located at each pallet-ready station. As the shuttle is completed, the code on the fixture is read and the part is identified. PAL uses this information to select the correct program and shuttles the part onto the index table at Station 3. The machining challenge here? Turn the flange OD and face, back face, and counterbore both ends of the workpiece. Parts of this configuration have long been confined to lathe operations with multiple setups and excessive handling. The solution: machine the part on a Kearney Trecker module designed to rotate the tools around a stationary workpiece. At this station, 2 turning modules are located on opposite sides of a 4-position index table. Each turning head is mounted on a servo-controlled slide to provide feed movement. Turning and facing in one setup is made possible with this unique Kearney Trecker designed head. 2 numerically controlled cross-feed slides are mounted on a rotating drum. A combination of drum rotation and cross-feed slide motion is used for facing and counterboring. Turning operations are accomplished by fixed cutter blocks mounted on either side of the slides. This station's geometric layout is basic to the integrity of workpiece dimensions. Both modules have been critically aligned on a common center line through the part to be machined, thus achieving a high degree of concentricity. Each turning head is 52 inches in diameter and is driven by a 60 horsepower motor. Since all axis movements are under NC, simple contouring can be performed by programming 2 axes simultaneously. Here, this feature generates a radius at the junction of the flange's rear face and the body of the housing, and deburrs the sharp edges from the turning and facing cuts made on the flange's front face. To produce superior surface finishes, these modules also are equipped with a form of adaptive control. As the facing cutter moves across the workpiece, the spindle RPM is continuously adjusted to maintain a programmed chip load. This constant surface speed feature is built into the control and does not require assistance from the operator. Turning on both ends of the workpiece is completed in the first cycle operation. Next, the part is indexed 180 degrees and only the facing and back-facing operations are repeated. After completing operations on both ends of the workpiece, the part is indexed 90 degrees and shuttled to the next pallet ready station. Again, the workpiece code is read by PAL. If station 4 is unoccupied, the part is shuttled onto the index table. The challenge at station 4? Rough and finish both front and rear bowl faces. The Kearney Trecker solution, a simplex version of the turning station we have just seen. The 40-inch diameter turning head is powered by a 60 horsepower motor. To perform the facing, 2 servo-controlled cross slides feed tool blocks across the workpiece. Cutter depth is provided by the head feed slide. To maintain a balanced inventory of finished parts, workpieces are alternately fed into the system, a front housing, then a rear. However, front and rear housings require distinctly different operations. The flexibility of NC is graphically demonstrated as it reduces these differences to a simple program change. Both programs are stored in the machine controller. Once again, this entire sequence of operations is performed without the assistance of the operator. After facing operations have been completed, the pallet is shuttled to station 5. Again, this transfer is completely controlled by the PAL interface program. The machining challenge at station 5: perform rough, semi-finish, and finish boring on both flange ends and the front and rear bowls. The Kearney Trecker solution, a rotary head indexer with multi-mission boring heads and a 72-position workpiece index table mounted on a feed slide. 8 single spindle boring heads are mounted on a 90-inch rotary table. A single 40 horsepower DC drive motor powers only the head in use. Heads are driven through a right-angle drivetrain. The drive is automatically disconnected for indexing. The feed slide, which carries the workpiece index table, is powered by a DC ball screw providing 17,000 pounds of feed thrust. The workpiece index table has the capacity to lift 10,000 pounds. This heavy-duty table can be positioned in 5-degree increments for a total of 72 positions. By using multi-diameter boring tools, Kearney Trecker engineers further increase the versatility of this machine. Each tool is capable of cutting several bore sizes. With just these 8 heads, without manual tool changing or operator assistance, this machine can complete boring operations on all 12 parts. 14 different bores are rough, semi-finished, and finished bored for a total of 42 operations. Kearney Trecker builds these rotary head indexers in either simplex or duplex styles. An example of the application of tomorrow's technology, producing today's parts. On the opposite side of the workpiece index table, an automatic gauging station checks the final accuracy of all bore diameters and counter-bore depths. Multi-probe electronic gauge heads are used to perform the actual measuring function. To check a part, the gauge head is inserted into the bore. Dimensional data is displayed and retained on a digital readout panel. If all the bores are correct to print, the part is moved to the next station. If the bore proves to be out of tolerance, a red emergency light signals the operator and the machine is automatically shut down. This checking method has another unique feature. If the inspected part proves to be not perfect, but within tolerance, a yellow caution light alerts the operator to the out of tolerance trend. A yellow caution light also appears on the readout panel. The number of parts the machine will pass in this near tolerance condition may be preset in the control. The machining challenge at Station 6: drill a series of holes on both flange ends and the bowl face. The Kearney Trecker solution, another application of the standard rotary head indexer. Here's proof of the flexibility of Kearney Trecker's standard modules engineered for the needs of the 80s. 8 heads, carrying a total of 188 drills, complete drilling operations on the whole family of workpieces. The 8-button code reader selects the programmed head. This reader is also under the control of PAL, and its operation is the same as the pallet identification system. Final head alignment is controlled by a hydraulically operated shot bolt located in the base of the indexer's table. The workpiece index table with 4 90-degree positions is mounted on a servo-controlled slide, which provides feed motion. Each head has a drill guide plate that is inserted into the finished bores during drilling. This coupling of the drill head to the part provides maximum rigidity. All drill heads are equipped with quick chain spindles and use preset tooling for fast tool replacement. These head indexers are not limited to boring and drilling. These same modules can be fitted with single-point boring bars, reamers, and tapping tools. After the part is drilled, it's shuttled to the unloading station. Here the part is removed and the empty palletized fixture is sent back to Station 1 on the pallet return system. The Kearney Trecker technology expressed in this manufacturing system has erased the established concepts of production time for these housings. Formerly, each workpiece required 8.5 hours of machining time. Now, Kearney Trecker has slashed cycle time to just 20 minutes per part, an astounding production rate, 7 times faster than previous methods. By applying this new technology, most medium lot size producers can obtain similar dramatic cost savings. Savings that were never before available to this group of manufacturers. This, then, is the technology of the 80s. An exciting concept made possible by integrating the flexibility of numerical control with high-volume mass production methods. A totally new approach to medium lot production. The flexible manufacturing system. Another dynamic result of Kearney Trecker's search for a better way.
We accomplished a measurable saving of 1,500 hours per month.
We are able to take a new design and get finished parts quicker.
Has changed our whole way of thinking in this business.
It enhanced our competitive position.
We have been able to get a job moving faster.
Increased productivity ratio of 5 to 1.
And we can have parts in less than 1 day, complicated parts.
The built-in accuracy has been a hit on the assembly floor.
Scrap has been practically eliminated.
We've experienced 95% uptime.
The biggest benefit that Crescent gets from Milwaukee Maddox is the reliability that it portrays in the customer's mind.
You've just heard the actual voices of men whose companies represent a broad section of our industrial economy. Regardless of the markets they serve, they have one thing in common. All have experienced increased profits and growth. We at Kearney & Trecker believe this enviable position is due to their management's decision to manufacture with Milwaukee-Matic. However, we want you to decide, based on the evidence they will present. Lawrence K. Mann is Director of Corporate Manufacturing Engineering Services at Curtiss-Wright. This aggressive company has had 7 years of experience with Milwaukee-Matics at their Wood Ridge, New Jersey plant, currently using 6 Model 3s, 5-axis, and 1 Model 2, 3-axis.
Curtiss-Wright is presently a first-tier supplier of a wide variety of aerospace components in support of commercial and military aircraft requirements. Through a continuing program of training operators and maintenance personnel, coupled with a thorough preventive maintenance schedule, we improved our uptime to its present level of 95%. We recognize 3 major benefits. These are reduced tooling costs, improved facility utilization, and minimum cycle time from customer order to delivery. Our total experience at Curtiss-Wright has been very rewarding. As an example, we accomplished a measurable saving of 1,500 hours per month on a single major engine component. We feel that this type of equipment is an absolute necessity in maintaining a competitive posture in today's marketplace.
In Grafton, Wisconsin, the Russell T. Gilman Corporation for the past 3 years has depended on Milwaukee-Matics to help maintain a competitive posture in their particular marketplace. The highly specialized art of designing and manufacturing of machine tool modules for special machinery builders. Our interview was with Gilman's president, Russell T. Gilman.
I believe that we are able to take a new design and get finished parts quicker by the use of the tape machining system. Well, the repetitive capability of the machine certainly does reduce scrap. I would also feel that it helps reduce the cost in the final assembly as the parts are more uniform. On a percentage basis, I would say that we are able to operate the machine approximately 80% of the time. This we feel is good, considering the fact that we have at the present time programmed over 275 different parts on the machine, and some days go into as high as 3 to 4 different parts.
In the aircraft industry, Milwaukee-Matic has revolutionized engineering thinking. A good example is the Berteo Corporation located in Irvine, California. This company has 5 years of experience with Milwaukee-Matics, currently owning 5 Model 2s and 3 Model EAs. They run 24 hours a day, 7 days a week. Lee Edwards is Bertea's vice president and general manager. And what's Mr. Edwards' opinion of Milwaukee-Matics?
We're installing another one in October. It's changed our whole way of thinking in this business. It takes the old 120-day lead time, reduces it down to something in the neighborhood of 30 days. It certainly reduces the scrap problem. It reduces the inspection time. Also has had a great impact on our shop planning, since we're doing so many operations on one machine at one time. On the Model 2s, the last 3 months, I think, have been less than 2% downtime. I think the first machine took over a job that had been running the old-fashioned method. I think it was 56 hours a body. It reduced it down to something less than 3 hours.
Just think for a moment what that means in terms of delivery and profits. Also in California, at Linwood, the Western Gear Corporation has felt the profound impact of 2 EAs, 2 EBs, and 2 Model 2s. This company supplies complex, precision, aluminum, magnesium, and stainless steel parts to the aircraft industry. We visited with Jay Davis, the manager of Western Gear's NC facility.
We settled on Milwaukee-Matic as our first step into the machining center capabilities by purchasing a Milwaukee-Matic EA in August of 1964. It enhanced our competitive position by allowing the machining of precision housings on the Milwaukee-matic instead of the more costly method of jig boring. Our mechanical uptime has been upwards of 90% on our Milwaukee-matic machining centers, and this is far above our projected expectations. I would say Milwaukee-matic has contributed to our lowered production costs by reducing the number of machine setups per part, reducing our material handling costs, compressing our schedule time, and producing parts faster with more repetitive accuracy. This in turn has reduced our scrap rate, our tooling costs, and increased our control of quality.
For the past decade, Milwaukee-matics have earned a reputation for their ability to make tremendous inroads in what was once considered normal overhead. We also talked to another California customer, Morrison Industries, a user of 2 Model EBs for over a year and a half. Our interview was with James Womack, manufacturing engineer.
With the Milwaukee-matics, we're able to control engineering changes and blueprint changes much better than we had been able to do in our conventional shop. We found that our uptime is running around 90% now. The Milwaukee-matics repeatability has all but eliminated our scrap problem. We have been able to reduce our production costs with the use of the Milwaukee-matics. We're able to maintain control of the shop time to the point where we can make money.
There isn't much we can say to top that statement. Now let's move our cameras over to the Midwest, to St. Louis, where Emerson Electric's Electronic and Space Division has applied the Milwaukee-matic concept for almost a decade, using 4 Model 2s and 3 Model EAs. Richard Fox is Emerson's Vice President of Manufacturing and has the responsibility for the production of systems for military and civilian aircraft.
In our constant endeavor to reduce manufacturing costs, we at Emerson Electric have found that the utilization of the Milwaukee-matic Machining Center has permitted us to greatly reduce inspection costs. We now rely heavily on a first article inspection and a very abbreviated sampling plan. And this, of course, has allowed us to reduce the cost of very large gauge programs that heretofore were required. We at Emerson utilize our Milwaukee-matic machining centers on a 3-shift basis, 7 days a week, and have, over the past decade, experienced an average of 78% uptime. In addition, of course, we've been able to eliminate a lot of the conventional machines and therefore save a considerable amount of floor space. It's curtailed the necessity for additional bricks and mortar, and the ultimate payoff, of course, is a increased productivity ratio of 5 to 1.
Another nagging problem that all manufacturers face is the salvaging of marginal parts. With its need for special handling, its slowdown on deliveries, and most of all, its continuous erosion into the normal profits you planned on in the first place. For comments on this topic, we moved to Seattle for a visit with the president of the Stearns Company, a customer with 1 year's experience with 2 Model EBs. George Stearns owns a job shop that produces precision aircraft parts and assemblies. Here's what he says about marginal parts.
Elimination of having to try and save marginal parts has been very important with the Milwaukee-matic. We just don't have these marginal parts, and lead time is very important after initial setup has been made, because it really means you set the fixture on, you put the tape in the machine and set your tools, and you're in business at that point. And we can have parts in less than 1 day, complicated parts. Our experience shows that we have approximately 95% uptime with the Milwaukee-matic. The Stearns Company has been able to take jobs that previously ran erratic from one time to another and stabilize the run time. The quality has been up and the inspection time down, thereby increasing the profit and reducing the cost of manufacturing.
We now move to Dover, New Jersey to visit with the Cameron Machine Company that produces slitters, winders, and rewinders for the paper, chemical, plastic, and metal industries. Cameron is well qualified to pass judgment on the application of Milwaukee-matics, having 6 years' experience with a Model 2 and 3 years' experience with the Model 3. Our interview was filmed in the office of Jack Ryan, Vice President of Manufacturing.
Our manufacturing operation at Cameron has been affected by Milwaukee-Matic to the extent that we can now produce many parts in one setup that previously required several machine tools, numerous setups, and fixtures. We have been able to reduce our lot sizes because of this and accept engineering changes without modification. Another reason for our purchasing the Milwaukee-Matic was the pallet shuttle system, which allowed us off-machine setup. The built-in accuracy has been a hit on the assembly floor, as there is less of the old plain muscle fitting. Parts made on the Milwaukee-Matic are always the same.
We call it repetitive accuracy. Now let's visit an Eastern firm which builds machinery for the production of boxes for the packaging of such items as cereals, frozen foods, and detergents. The International Paper Box Machine Company at Nashua, New Hampshire, has had 3 years' experience with 2 Model EAs. We visited with Jerry Fontaine, International's production manager.
With Milwaukee-Matics, we no longer require the expensive and accurate fixtures that are required with conventional machines. It has reduced our tooling cost and extended our tooling life. Our manufacturing lead time has been shortened. We utilize these machines 19 hours per day. Having 2 the same, we are quite flexible. The accuracy of these machines give us the product quality we require with a minimum amount of inspection. Scrap has been practically eliminated. The cost reduction ratio we have encountered with Milwaukee-Matic over items that were previously manufactured conventionally is approximately 5 to 1.
No wonder companies find that the Milwaukee-Matic manufacturing concept rapidly becomes the real power behind their profit picture. Now let's visit the Cherry Burrell Corporation in Cedar Rapids, Iowa. 14 months ago, this company purchased 1 Model EB for the manufacture primarily of stainless steel parts used in processing equipment for the food industry. Our interview at Cedar Rapids was with Al Hirschfeld, the manufacturing manager.
At Cherry Burrell, we are in the midst of a product diversification program, and the Milwaukee-Matic has provided a decided assist in the introduction of this product. For example, on Cherry Burrell's new carton filler line, we have probably realized in excess of 90% savings over conventional tooling costs. Cherry Burrell's experience in the operation of this equipment has been far better than we anticipated. As a matter of fact, we've experienced 95% uptime, and that includes downtime at the time of installation 14 months ago. Cherry Burrell is pleased with the reduction in manufacturing costs achieved through our Milwaukee-Matic. An outstanding example would be this lever, which had a previous cost routed through conventional manner of $44, and a present cost with the Milwaukee-Matic is $6.08.
That represents a saving of $37.92 per part. That certainly makes Cherry Burrell a very tough competitor in anybody's market. Crescent Precision Products, located in Tulsa, is a very unique job shop providing the aircraft industry with specialized precision parts and assemblies. 4 years ago, this company purchased their first Milwaukee-Matic and now have 1 Model EA and 2 Model 2s, 5 Model EBs, and 1 Model 3B in their shop. We talked with Clyde Miles, Crescent president.
In 1964, we went to K&T to attend a sales seminar on the EA Milwaukee-Matic. They took us through the plant, and in this plant tour, we saw various data input stations of IBM's. We looked at these and asked to talk to some of the computer people that was having something to do with your electronic data processing system. So K&T didn't only get us started in Milwaukee-Matics, which has added an awful lot to our capabilities to deliver items on time. They got us started in controlling our whole plant on a computer. we individually machine load each operation to a specific machine. It tells us whether we are operating on schedule for a specific delivery date. We have one of the most thorough computerized control systems, I think, of any plant in the United States. Due to this, K&T has had an awful lot to do with our advancement here at Crescent. I don't know whether they really realize how much they did for us at this one seminar. But really, it led to quite a growth at Crescent in 4 years, because we started in 1964. Our first machine was delivered in here in October of 64. At that time, we had 50 employees. At the present time, we have over 400 employees. And to do this, and by this time in 68, without any additional capital coming into the company, and doing it the hard way, I think you'd have to say they contributed a lot to our advancement.
You've now heard the comments of these businessmen who represent a cross-section of American industry. These companies collectively have over 46 years of experience in this new metal removal technology. They're tough competitors in anybody's market, because using Milwaukee-Matics, they can rely on repetitive accuracy, reduced lead time, lower inventory, no scrap, fast engineering changes, positive quality control, parts to order, reduced tooling costs, predictable profits. With Milwaukee-Matic, you too can profit from the same benefits that make these 11 companies and hundreds of others tough competitors. It always pays to listen to the voice of experience.